Okay, Radioactivity, Lecture 56. Write the names and symbols of all the subatomic particles we'll be dealing with. And, well, before we talk about those, let me just talk about the nuclide symbol. This was discussed a long time ago, I think Chapter 2, in 1170. But we have X represents the element symbol, and then we have the atomic number that we'll also think of as the charge. The atomic number is the number of protons, and so that is the amount of charge as well for the nucleus. And then A is the number of, so this is the number of protons, and then A is the number of protons and the number of neutrons, and that's the mass number. Kind of running out of room here. So you should know that. That's what we're showing here are these nuclide symbols. So for the proton, hydrogen, it's one proton, and its mass number is 1 because there's no neutrons for just a basic proton. We can write it as P, 1 and 1, or P+. The neutron is 0 because it contains no protons, and so its charge is 0. And then it has a mass number of 1. Electron, it has a mass number of 0 because it's so small, it's 1/2000th the mass of a proton, so we just assume it's 0, or round it to 0. And then it has a -1 charge because it doesn't have any protons, it has a neutron. And just looking at some, we can also call it the beta particle. A beta particle is just an electron that's moving very quickly. It has a lot of kinetic energy, and that's what they usually have coming out of a nucleus that's decaying. We have the positron, which is the antiparticle of the electron. It has a +1 charge, but 0 mass, and so we can also write it as beta 0, 1. Gamma particle, a gamma photon, has 0 charge and 0 mass. Or I should say 0 rest mass. And then deuteron from deuterium has 1 proton and 1 neutron, so 1 and 2. Tritium or tritium is 1 and 3, has 2 neutrons. And then the alpha particle we're going to see a lot of is, I should say the deuteron can be written as a lowercase d and tritium as a lowercase t. Usually they have to be well into context here. You need to know why you're writing that D, but it will be very clear in the context we're using these two symbols in. Alpha particles, He 4 and 2, it's because it's 2 protons and 2 neutrons. We can also write it as with an alpha symbol and sometimes just as alpha. So there's a lot of different ways of doing this. So you have to look through the book, do these problems because they come up with all these different forms of these symbols, and that's just how it is in this field of study. So you should know the different forms. Alright, now we're going to use them. Fill in the missing species in each nuclear equation. So that's what we have here. Rather than a chemical equation, we have a nuclear equation. So we're not trying to balance the elements, because the elements are changing. That's going to be the whole point of these nuclear equations, is that we're changing from one element to another. So we don't look for one radium on this side and one radium on this side. It won't be radium. We've removed 2 of the protons, so it's going to have less protons. So what we do, instead of trying to balance out the elements, we're trying to balance the atomic number and the mass number, because that can't change. We can't lose the mass, we can't lose the charge. It all has to be in there somewhere. So what we do is we look at the bottom. We have 88 and we have 2 here. If this new element has 86 as its atomic number, then 86 plus 2 is 88. And then 4 plus something gives us 226, so this is 222. 86, then we can look in the periodic table. 86 is radon. And these are so similar, radium and radon. Radon gas is the radioactive gas that seeps into basements from underground. There's radioactive source is underground. And the radon gas is the thing that poisons people in their basements, and then you have to go to the hospital where you'll see an RN, registered nurse. So that's how I remember it. You can remember it any way you want. But these two are very similar to each other, almost the same mass. They're really near each other in the periodic table. They have almost the same element symbol, so they can be confusing. Okay, so, or can be confused. Okay, so we have this here. Now we just add them up. We have 2 minus 1. So just make sure you have that's a beta particle. That's an electron escaping. So 2 minus 1, that's 1. So this must be 63. So 63 plus 2 is 65, minus 1 is 64. Then 4 and 0. So 4, so this would be 156. So you can, I'll make sure those match top and bottom. And then we have 63 is, where are you, 63? Europium. And we'll get to know a lot of these element names. I'm not going to require that you know all the element symbols and names for all of the elements above 92, or that are in the lanthanides and actinides, but you'll learn a lot of them as we go. Here we have 3 times 0, so this is still 92, and then this is 3, so this would be 235, uranium-235. So we got to be careful. So I put everything in here as far as we have negatives, positives, we have 0 when we add these things up. So just add them up top and bottom and you're all set. Okay, so when we're given a set, we can, an isotope, we want to know whether or not it's radioactive. There are 3 tests that we can run. They're very, very basic. Somebody who is in this field of study will probably know most of the radioactive elements that are common. But if you came across 2 and you weren't sure which one was radioactive, but one of them was, you could use these 3 tests. So we have, according to the rule of magic numbers, which one of the following should be stable. Now the magic numbers, what this means is that if you have a nuclide or an isotope that has one or more, one of the magic numbers for protons, or one of the magic numbers for neutrons, or both, it should be fairly stable. As an example, 2 and 2 here, that's helium, that would be 2 neutrons and 2 protons. The helium nucleus is about as stable of a nucleus as you're going to find. So that's a nice easy one. 8 and 8, that's oxygen. 16, very stable as well. So, but if you have, so what we want to do is just compare the nuclides. If one of them has none, and the other has 1 or 2 magic numbers, then that's the more stable one that has 1 or 2. If one of the nuclei has 1 magic number and the other has 2, then we'd have to go with the 2. But we normally want to make a big distinction here, so let's take a look here. Calcium, it has a number of protons is 20, neutrons 20. Those are magic numbers here. For potassium, 19 and 21, so it doesn't have any magic numbers at all, so we go with this. Now this is very, 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 very basic, but as far as the rule, but it's the one that we know, this one that we learned. If you're going into nuclear chemistry, you'll look back at this and say, oh yeah, that's nice. And it does, but like a lot of the rules that we have, it covers a good percentage of the nuclei, and then there's lots of exceptions. So, and you'll see the exceptions. So if you find stable nuclei and they don't follow the magic number rule, don't be surprised. But on the exam, if I give you 2 nuclei and I'll ask you to, and actually most likely I'll give you a set of nuclei or pairs of them, and I won't state which rule applies. You have to apply whichever one you think works. Okay, then the even-odd rule, what we find is that that if you have, as far as protons and neutrons, even is the most stable, and then you have even odd and odd even, which are the next most stable, and odd odd are the least stable. So if we find an isotope that has both protons and neutrons as even, then and the other isotope has odd, 1 odd or 2 odd numbers for the protons and neutrons, even wins out. So And there's a table in your book that shows the number of stable nuclei. For even, there's 157 stable nuclei. Even odd, 52. Odd even for protons, neutrons is 50. And then both protons and neutrons being odd, there are only 5 that are stable. So again, there's exceptions to this. They don't have to be, isotopes don't have to contain even numbers, one or the other or both, to be stable, but it really helps. So let's look here. We have phosphorus, 15 and 15, both odd, 16 and 18, so both even. No magic numbers here, and that's how I'll generally do it on the exam. So you can't look at magic numbers. This is really all odd, even odd, or the even odd rule. So this would be the most stable. Am I asking which should be stable? Yeah. Then this is the band of stability. Actually, is the best way of determining what is stable, but they don't give you a really nice table to work with. It's a small one, and that's what I'd give you on the exam. When you measure the protons versus the neutrons, or you graph them, here's the line that shows if you had the same number of protons and neutrons. So number of neutrons, capital N, number of protons, capital Z. And this band, if you look in your book, it shows all the dots of all the isotopes that we have that are stable. And at first, like helium, there's the same number of protons and neutrons, 2 and 2. And it follows that, it'd be right on this line. But as you go along further up into the higher numbers of protons, you need more neutrons to keep the isotope stable. You need more of the neutrons separating out the protons to keep the nucleus stable. So we deviate from this this straight line, or this N is equal to Z line. So if the isotope is found in this band, then it's stable. If it's found outside of this band, it is unstable. Above here means that we have too many neutrons. This is called neutron rich. Down here is called proton rich, or neutron poor, and this would be proton poor regions. So on the exam, since a lot of the isotopes that are unstable are riding this line really close, they're just outside of the band of stability, it's hard to tell. So I give you something that's relatively crazy like this. So the nitrogen, we have 7 protons, 7 neutrons. So they're both odd, but they'd be right on this line right at the bottom. I haven't drawn the markings here, but this is like about 20 and 40, so yeah, it'd be right on that line. It'd be right in the middle of the band of stability, and then 7 and 30 would be, so 7 protons and then 30 neutrons would be way up here. So I'd make it very obvious that it's outside of the band of stability. And just looking at it and saying, well, you have 7 protons here, 7 and then 30 neutrons, seems like that would be unstable. So those are the rules that you would need to use to determine which of a pair of nuclei are unstable.